After the excitement in the forest last week, I thought I'd better get away somewhere safe to this lovely Antipodean beach.
Equals wallet. If not, then go sub. Input knife. Poke, 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 poke.
Oh no! A thug! And he's threatening me with a programming language.
There's not a programming language. This is a programming language.
I'm saved! Thank you. No worries, mate. Go grab yourself a tinny. Good day, coppers. William Horace Tang here, and I'm here to show you all about Z80 machine code. Now don't come to war prawn with me, mate. Today's book is Spectrum Machine Language for the Absolute Beginner, because we're absolute beginners and we're absolutely sure. And it's edited by William Tang, the famous William Tang of Horace fame, published by Melbourne House in 1982. It goes over machine language, again, from absolute beginner territory, and gives us a program so we can get the machine code into memory. This program is called EZCode and is copyright 1982 by William Tang and A.M. Sullivan. Pictured here, presumably in a drama series all about his life. So once it loads, it initializes, and I've changed the beeping, which was originally the same tone 200 times, to a slowly increasing, exciting, beepy thing. It's just initializing the arrays of the source code that you will need to type in. So what does it do? It lets you enter machine code to any address from 31500 upwards. It's done this by cramming it as much as it can, but it's still a reasonably sized program, even though they've saved a fair amount of space by not using 0, 1, 2, 3 or 4 as numbers, but in fact as variables, which is rather clever. So we're going to load our code into 31500, and we then get to enter some source, but you can't use assembly language. Oh no, it's going to be machine code bytes. But the advantage of this program is you get to use line numbers. So here I'm loading the HL register pair with 4000 in hex, which you have to enter in reverse order as 0040, because you enter them as low order byte first. Line 5 is going to be load into register pair DE, which is at 11. The hex value 4001, which again you enter in low byte order first. Line 10 is load into register pair BC, which is 01. The number 6143, which in hex is FF17. 6143 is the entire size of the screen, I think. Then line 15 is load into register A. The value FF20 is load into the address pointed at by HL, the value currently in the accumulator. What we're then going to do is issue a command called LDIR, which is load immediate repeat, I believe. So that will basically copy everything from one set of from the address in one register to another, and after you've done that, subtract 1 from register pair BC until you've run out. Now on line 30, we're going to load register A with the value 7F, because what we're going to try and do here is look out for someone pressing the break key. So to do that, you load register A with 7F, which is the line of the keyboard you want, and then on line 35, we're going to do in register A for the value FE, which is 254. So that's going to check the bottom row of the keyboard. We're then going to look at line 40. It's going to be AND A, so we're going to be looking for the existence of is bit 1 on. The reason you use AND 1 rather than checking the bit itself is bit instructions are rather expensive. So we're saying is bit 1 set? Or is bit 1 not set, actually? So it's not set if you press it. And if it's not set, we need to jump back to the checking the keys, which is a going backwards. Going backwards, you have to use a negative number, which involves using 2's complement. You could look it up in the back of the book, If you do -2, you'll go back to where you are now, which is not what we want. -4 will go back the line to the AND one. Again, what you really want is -8. And you could look it up, or this program lets you do L30, which is go to line 30. So if you then add extra lines, it'll sort it all out when you come to assemble it. So this is just the source code so far. It's byte sort code, which is all held as a string. Finally, line 50 is C9, which is return, so we quit. So what we then need to do is issue the command dump, which will then go through the source listing and copy the bytes into memory, starting at address 31500. It keeps an eye out for any of the L instructions, which are line numbers. So it's found one. Line 45 is a jump to line 30. So, oh, by the way, yeah, line 30 is 3E7F. Is that all right? Yeah, that's fine. So we can now look at the instructions at 31500, and you'll see at 31520 is 20F8, which is jump relative on not 0 to -8, which is back where we were, followed by C9. You press M to come out of there, then we can run the program, and it basically fills the screen with blue, which is nice. So we looked at EZCode. We can forget that. We're not going to use that. What we are going to use instead is another program, this one by William Tang and David Webb. This is called HEXLOAD. The reason we're using a HEXLOAD is EZCode can only store 200 instructions or about 800 bytes of machine code, which isn't going to be enough. HEXLOAD, however, can store a lot more. You can input your machine code anywhere from memory location 27,000 up, so that gives you about 5k for the 16k spectrum. The addition I've made here is to add a checksum routine. They do provide a checksum routine in the book. The idea is you add up all the bytes you put in and the number should match what you've got. So here's an example of us entering the code. We are given all the code for a program called FREEWAY Frog. And the very first thing you need to do is to set up the database. This is the graphics. They're not using user-defined graphics because they're not going to be enough. So what you have to do to get HEXLOAD to work is you enter the address you start off with, and then you carefully enter the hex codes from the back of the book. It gives you a range of addresses, and the first section you've got frog ship, left bike attribute, right bike attribute, left car attribute, right car attribute, left truck attribute, right truck attribute, and blank. There are 986 bytes in all of these sections. You can enter individual bytes as they are, or you can enter a series of bytes. However, if you make a mistake, it'll tell you incorrect entry. What I tried to do was make it beep to you in flashed or something. There isn't enough memory to do that. It's really down to the wire. So it knows if you enter an odd number of digits, it's wrong, therefore it's incorrect entry, or if you enter something that isn't a valid hex code. Because I'm running this on emulation, occasionally the computer itself does something and it doesn't quite pick up entering a key, which is a bit of a problem. So what we're entering here, though, these bytes are the frog. Well, the first actually 2, 4, 6, 8 bytes are the addresses of the different frog. Here we are, I've entered something wrong there, and I've not noticed. And eventually I look up from the book and realise, oh, poo. What you can then have to do is work out where you went wrong and then overtype it starting again. Unfortunately, the book gives you the addresses in hex. The program accepts addresses in decimal. So the program lets you list the machine code in memory, try and spot where the error is, so you can actually get the address you need to overtype and start again. So after entering everything successfully, you get to make sure you've got it all right. So here I'm entering a long string of hex characters because I'm feeling brave. If I get one of these wrong, it will tell me incorrect. And then once you've completed, you enter M to return to the main menu. And then you can do checksum. We're going from address 27055 up to address 27190, and this should add up to 18,085, and it does. After doing all of these, you save this to tape as shapdb, and this is the 32 different shapes we need for the game. Now we're on to part 2. We're actually sorting out the actual program. So in the initialization section, we need to enter a number of little subroutines. The way it works, you build up subroutines. The first subroutine we enter is clear sqr, which is at 29399, and clear sqr is the clear screen routine. We're not using the ROM routine. Perhaps they didn't know about the ROM routine. Perhaps the ROM routine isn't very good. But it's at 29399, which in hex is 72D7. And the checksum should be 5236. If not, we've done it wrong and have to try again. Back of the net. We now have to enter draw highway, fill highway, and final. And then we have to enter the init routine. The init routine is the thing that starts the program. However, when we use the init routine, we had some issues with the init routine. Init routine starts at 28547. And we enter all the code. It's only 140 bytes. Unfortunately, I kept making mistakes. And when you make mistakes, it's very tricky to work it out. So this should be 11996. It is not. I've got something wrong. So let's try again. So going from 28547, and this should be 11996. And it's not. This should be 11996. Cashback. Now, having entered it correctly, we then need to change it because we are doing various calls to subroutines we haven't written yet. So the book says, here are these addresses, which can give us in both hex and decimal. You have to enter 3 bytes of zeros to say, look, don't do anything, because you can't call them because we've not written them yet. So now we enter a little testing routine, and when we run it, we should get the screen go black and 4 white lines appearing on the screen. There's no checksum for this. So we're now going to run this little routine by doing randomize USR 32000, and we should get the road. Yes, we do. 2 white lines and a dashed line. Now we're told to enter the line up and draw frog routines and to check the checksums. Unfortunately, we only get a checksum for the line up routine, but not for draw frog. Fortunately, you can find draw frog in the code and type it in and hope you get it right. I got the checksum correct for lineup, which is 4325, but draw frog, I had to hope for the best. And you update the little test program, and what you should see is the frogs there, and you don't. The problem is, what you're meant to do is load all the databases that you did in part 1, the shapes, objects, and general database. It doesn't tell you this. So what I'm now going to do is load those, and then load back what we've got already. So now we run it again. Randomized use of 30,000, and we now get 5 frogs. And the last bit of part 2 is to input the dis, ask, and the screw image routines. Again, doing the checksum for these, and then making sure we call everything properly. These are checksum is 1855 and 38580. And when we run this, we should get the score and the high score as well. Yeah, and we do. We've got score, high score, 5 frogs, and a road. We are cooking with gas.
You great galah!
So now into stage 3, which is regular traffic. In this section, we're going to add in traffic control, which is everything apart from the police car, which is traffic control, regeneration of traffic, moving the control of the traffic, drawing it, and determining the right shape. So the first thing we need to do is type in 2 routines, which is draw and R shape, and do the checksum. So the checksum from 29193 is the draw routine. It should be 13923, and it is. I'm getting good at this. Also need to load various modules in the right order: the database routine, the init routine, the regular traffic routine we've just typed in, and save those into a frog module of 4000 bytes. And then when we run 32,000, we should see the screen setup and a right truck on the top lane. You save lots of different bits, all in the same memory, and you slowly overwrite each other in the correct way. If you do it right, it's fine. If you do it wrong, though, it all goes a bit wrong. And it's machine code, so it's always best to be cautious and snapshot yourself. So this is the frog routine. We're going to 27,000 and it's 4 bytes, less than 4K. So now I'm going to run the little test routine with randomize USR 32,000. We should see the road and a truck. What we actually see is some random blobs on the screen. The lines look about okay, and we've now corrupted the basic program. So something has gone horribly, horribly wrong. Horribly wrong indeed. And yeah, it's just generally hosed. So we're going to try it again, but this time be a bit more cautious. So we've now entered again properly and very, very carefully with all the checksums. And we now run it and we get indeed a single non-moving truck, 5 frogs, the highway, score and high score. This is good. It doesn't tell you to enter the random number routine, which you absolutely need to do. But it's a bit of a problem. Otherwise it wouldn't work. So I entered it anyway because I'm clever like that. And when we run it, we should see all the traffic actually moving, but at an incredibly fast rate. This is because there is no delay between the program cycles. But we have moving traffic and frogs. Now on to part 4, where we develop the police. So the police car moves, is generated randomly and enters with its siren going. It moves every cycle, so it's incredibly fast, and it ignores traffic and overtakes traffic and just goes super, super fast. So what we need to do is save what's underneath the police car in order to put it back later on. So the first thing we need to do is enter the police routine, which is rather large. It is 148 bytes of machine code. Having done that, we enter our little test routine to test the police routine, and we have the police car moving along. There's no siren as yet, that's to be expected. See how fast the police car is going. We can then edit the test routine to add in traffic to see how it does. To do that, we changed one of the jumps from jump relative not 0 move 1 to jump relative not 0 move, which involves faffing around with 2's complements, which is tricky. But here you can see the police car is overtaking the other traffic, and it is going faster than the lorries, going faster than the cars and the bikes, but other traffic is queuing up. We're now going to add the routine to restore what was underneath the police car, a routine called res PC, which is about 50-60 bytes or like, should have a checksum of 11011, which it does. We update the test routine. As we go along, they give us the new hex codes for the hex routine, but not the ones you've already done. And here we can see we have the traffic and the police car overtaking the traffic at incredible speed. This is what a 3.5 MHz processor can do for you with machine code, not in BASIC. We're now adding in the siren routine. So we'll enter the siren routine and do the checksum. Again, they don't tell us where the siren routine is. You can find it, but they don't tell you the checksum, which is a bit of a problem. We then update the test routine and try it again, and it doesn't quite work. Oh, we get a police car, but no traffic. This is because I've got the 2's complement wrong for the jump. After fixing that, we get traffic and a police car moving the right speed. You can turn the siren on or off with the enter key, but the traffic now moves slowly because the lorries are slowing everyone up, but not the police car. Nearly there. Part 5, we now finally get to move the frog. We have to handle frog movement, saving what's underneath the frog and restoring what's back when the frog moves. So we type in 7 routines, about 400 bytes. And we find we can now actually move the frog right, move the frog left. We have traffic, we have police. We can go up, we can go down. Score doesn't go up. So let's try and cross the road. Yeah, it's all I can find. Go up, go up, go up, go up. And get to the top of the screen. And then, on to the next frog, are we? And then move along. And again, we just move on to the next frog. So we've died, but nothing happened because we haven't entered the frog dying routine yet. So once you enter the frog dying routine and the score routine, and the frog tone routine, we get a little bit of music. So we are now ready for the final chapter. The final bit is called control, where we develop the control routine for the program. We see here the final typing it in, And the control routine is pretty much now identical to the test routine we were using, except it starts at 27,000 because we're not using it as a test harness anymore. We just added a few more bits, which is called, to make it all nice and tidy. And then do the checksum, and it from 27,000 up to 2754, which is 8427. It's 55 bytes. It's basically a collection of calls and loops. And then also have a little routine called over, which checks to see if you got the high score. And that leaves it at address 3686 to 3717. And having done that, you'll have typed in the 4,000 bytes of machine code, or hex, correctly without getting any of it wrong. So we save the whole thing to tape as machine code, and now we are calling it Frog because we are now ready to play the game. This is the finished product. What I have done here is added a loader program. It's a machine code program, so you should load quote code. To save doing that, I've just done a little loader program which will load the code for you and then run it. And if you're doing a loader program, you might as well have a loading screen. So I created a loader screen thanks to the free pictures from pexels.com and ZX Paintbrush and GIMP. So give a nice little loading screen for the game. The loading screen is in fact 50% larger than the game itself. The game is only 4K, the screen is about 6.5. But I think it's worthwhile having just for completeness. The only change I've made to this game is I've changed the keys from 1AIP to QAOP, as you discussed, and let's give William Tang his credit on the lovely loading screen. Look at that, marvellous. And now we actually load the program itself, which takes about 25 seconds or so because it's really small. That's the power of machine code. Let's get started. So we are the right-hand frog on the bottom. So there's various types of traffic. There are yellow cars, there are red cars. The cyan cars are police cars, and I'm dead already. And the police cars, have their siren. You can turn the siren off with the enter key, but I like having the siren on. Obviously, normal traffic queues up in traffic jams. The police, though, overtake. And are a lot faster, so you can watch out for the police. However, there only tends to be one police car at a time. You have a safe zone on the white dotted line, and can then make a break for victory. The trucks are slower, but bigger. It's one frog home safe. You gain points every time you go up the screen. You don't lose points by going down, so if you really wanted to, you could wiggle back and forth on the side of the road and get a huge score. We're not going to do that, at least not much. That's 2 frogs home safely, 1 frog dead. So amble across the road. Here comes a truck. Can we make it to the safe zone? Yes, we can. Can we cross behind the red car? Looks like we're good, we're good. And that is another... Oh, no, little cheat there. Extra point. Frog touchdown. And the last little froggy. Oh, watch out for the police. And can we make it into the safe zone in time? Yes, we can just. Because it's all cased on character movement, so 8x8 pixels. This works quite well though. The lorries, the cars and the bikes are different speeds, but they will queue up behind each other. The police just overtake everybody with their little flashy sirens. And that's our last frog safe for a score of 1260. But now we're going to go for a no death clear. I've managed to get a score of 1290. We'll be playing for about 20 minutes or so. The key thing is being patient. You want to be on the left-hand side as far as possible to cross the first lane, amble across to the right, and then you got the maximum amount of notice for police cars and bikes and whatnot. I've got a nice space coming up, so I think I can make a break for it, and we are safe for the first frog. To go before this, I lost the last frog, which is annoying because I didn't quite get the high score. So now rush to the middle line, and we're safe. So there's not quite enough room to cross in front of the lorry, because he'll just clip our back legs. Just be patient, and if we had crossed, the police would have killed us anyway. So wait a little while. After this red car, though, we should have enough space, unless there's a police car. There's no police cars, let's make a break for freedom. Ooh, the Rozzers nearly caught us. That's 2 frogs safe, 3 frogs to go. There's plenty of space. Can we make it? Can we make it? Yes, we can. Ooh, ooh, ooh. So, the motorcycles are fast, but only a 2x2, so they are easy to avoid, provided you can see them coming. 3 frogs are safe. Can we do a no-death clear? Oh, I'm going straight for the middle. There we are. There's enough room to cross, provided nothing appears, and it's a high-risk strategy there. So if we move further to the right, you get more of a warning. We have 2 motorcyclists and a police car, but now we have lots of space to amble across for 4 safe frogs. Also, if this is a freeway, you think we would be in America. In America, they drive on the right, but on this freeway, we seem to be driving on the left. Oh, nearly there. Motorcycle nearly caught me. Oh, well, worrying about inconsistencies in the code. Now there's a gap. Motorcycle. I think there's enough space. And here we go, provided there's no police car. Our score goes up. And that, my good friends, is a no-death clear of Freeway Frog as advertised. Thank you for watching. Thanks for watching, Brucers and Sheilas. Why don't you settle back, throw another Horace on the Barbie, and click that like button. Ta-ra!